So now let's take a look at conjugated dienes. Here I have an example of 1,3-butadiene. And if we think about the molecular structure of 1,3-butadiene, we see that all four carbons have p orbitals, and of course I can label these four carbons 1, 2, 3, and 4, and based on the resonance, based on the Lewis structure view of it, we say that there's an overlap of the p orbitals on carbon 1 and 2 to form a pi bond, and there's an overlap of p orbitals between carbon 3 and 4 also to form a pi bond. But what's to say that you can't form a kind of a pseudo pi bond between carbons 2 and 3? And that's really what conjugation is. It's a 2p overlap between those two carbons. And we say that it connects those carbons or conjugates the double bonds so that they are somehow linked together and stabilized. So the question is, how much pi character does the C2-C3 overlap actually contain? Well, we can tackle this this question by one of two main views. The first view being resonance, and the second being molecular orbital theory. So let's take a look at the resonance view of this question. If I look at 1,3-butadiene, I know I can draw a few resonance structures of this. So the first resonance structure that I can draw is simply moving electrons, where I'm taking electrons from C1 and C2, placing them onto C3, and then the pi electrons from C3, C4 going onto that C4 carbon. And the result is that I get this separation of charge, where I have a cation on the left and I have an anion on the right. So this is not the most stable resonance structure, but it is a resonance structure that I can draw due to all of the pi systems, right? And of course, I could take that and I could do the reverse of that, and I get a second resonance structure where now I have the negative charge on the carbon on C1 and the positive charge on C4, right? Now, based on what we learned in chapter 12, I can actually, instead of doing a heterolytic movement of electrons, I can do a homolytic movement of electrons, where one electron from the C1-C2 bond goes to C1, the other electron goes to form a double bond between C2 and C3 with a pi bond that's being shared between C3 and C4, and of course the last electron is going to C4. And I end up with a diradical species. Now if I look at all three of these resonance structures, I see that they all contain a double bond that is actually between C2 and C3. And so it says to us that, so resonance view says to us, well, there's got to be some type of double bond character in this. Now, having said that, these three structures are not the most stable structure, and indeed, the traditional view of 1,3-butadiene is still the best resonance structure of 1,3-butadiene, and yet, this tells us that there is some pi character that's being involved. Thinking about the molecular orbital view might be a little bit more complicated, but we can simplify things quite substantially if we think about treating that conjugated double bond as two ethylene molecules that are actually overlapping with one another. So all I'm doing is looking at the pi system, I'm not really concerned about the sigma system in this scenario. So all I'm going to focus on is looking at the pi system. So if I think about ethylene for a second, I know that ethylene has a pi orbital and it has a pi star antibonding orbital. And I know that in that pi bonding orbital, the two orbitals are in phase with one another, and in the pi antibonding orbital, the two orbitals are out of phase with one another. Right? So I'm going to take that and I'm going to combine two of these, right? So on one side I have one ethylene, on the other side I have the other ethylene, and I'm actually going to mix them. So the first thing that I'm going to do is I'm going to take the two pi orbitals, the bonding orbitals, and I'm going to mix them, right? And this results in two bonding orbitals still, but the character is a little bit different. We're going to take a look at how they're different in just a little bit. And so I can do the same thing with the pi star antibonding orbitals. I mix them together, right? And I end up with, again, two antibonding orbitals that have a little bit different characteristics and energy. So let's take a look at the pi bonding orbitals first. So when I mix those pi bonding orbitals, I can get a mix of those orbitals where all four orbitals are in phase with one another. And this is where we would say they're all conjugated to one another, right? And so that's certainly going to be the lowest energy, right, where there's no nodes involved in the orbitals or between the orbitals. Now, another way that I can mix them is if the pi bonds from ethylene on the right are out of phase with the pi bonds of ethylene on the left, right? So again, I still have some bonding character. There's a bond between the two, two of the carbons and then two of the other carbons, but there's a node in the middle. Now, likewise, I can mix the antibonding, pi star antibonding orbitals, and the mixing that occurs at the lowest energy is when I have two that are in phase, and then of course the outer ones are out of phase. And then of course at the highest energy, I have it where they're all out of phase. So what this produces is so there's a node at the highest energy bonding orbital. There are two nodes in the lowest energy antibonding orbital, and there are three nodes in the highest bonding anti-orbital. Now, there are a total of 4 electrons in this system, and so we have to think about how those electrons are going to be filled. 2 are going to be filled in psi 1, which we call the pi plus pi, and then 2 of them are going to be filled in the psi 2, which is the pi minus pi. So we see that the psi 1 and psi 2 are both bonding orbitals, that psi 1 is what we call completely conjugated, and psi 2 has one node, so it's not completely conjugated, but it has the traditional, we would think of it as the traditional bond between carbon 1 and carbon 2, and then bond between carbon 3 and carbon 4, right? Now, interestingly, if we think about the HOMO, this would be the HOMO, right? This is where the electron, so this is the highest orbital where the electrons reside that are going to be involved in bonding.